Okay. Um, this is just a miscellaneous kind of uh, stream where I wanted to talk about some science. There's a lot of things, that people talk about in science. Relativity. This is going to have to do with relativity. So if you're not interested in that, um, just be advised. But I do have a debate scheduled for with Gavin on the 31st of this month, January. I guess around 8 o'clock or something. I'm not sure, but it's going to be on the age of the Earth. So we can just keep that in mind if you're interested, of course, watching two people talk about the age of the Earth. But anyways, I have a lot of videos that I talk about the haplogroups. I've pretty much nailed it down. It's a little bit hard trying to get the Hamitic haplogroups correct because they're all over the place. You know, they don't know what's connecting to what, but they have an idea of what connects to what. So we basically have the North Africans, the Mitzrayim Egyptians, and the Cushites are kind of hard, but believe it or not, the Canaanites are kind of easy. It's a group called Z830, and it's a whole bunch of different haplogroups that are like from one tree, which are outside of Africa. They're basically Arabia, Anatolia, Greece, and places like that, which would be the Canaanites. To me, it just screamed Canaanite because I saw one E3M123, and to me that just was all Canaanite. And there's a whole group of them all throughout, Saudi Arabia and Anatolia and Levant, of course, and Greece and places, and North Africa and stuff. But it's clearly, to me, the Canaanite group. There's clearly a North African group, clearly an Egyptian group, because the Egyptian group, of course, Mitzrayim had a number of sons, which I don't know which is which, or which group is which. Somebody who's a part of that group could be probably more interested in finding out for himself which line he belongs to, and they could probably be easy to figure out for himself, but I'm not there yet. Yeah, I could, might be after a while, but this all takes time to to assimilate all this information and everything and what it means, because the other groups I have down pretty well. K is pretty much absolute. Q is absolute. Of course, K is Tubal. Q is Madai. R is pretty much, nailed in place. That's Gomer. His sons Ashkenaz, Riphath, and Togarmah. Meshach is all the way up north. That's pretty secure. O is Magog. That's China, all over China. In other words, it went north and east, or went up around the Caspian Sea, either above or below the Caspian Sea, out east. That's Magog. And other places. A lot of these groups, of course, they go more than one place. For example, Q, Madai, is known as the Medes, in the area of the Medes. Madai went into Europe as well. And I was wondering how Madai got into Europe, the cube got into Europe. So, and when you know the history, then it all fits into place. Tubal was said to have settled in Italy. I looked in Italy. Yes, Tubal is there to this day. About 8% in central Italy, which is a huge mark, huge percentage. From ancient times, people living there to this day with a K, paternal Y chromosome. So a lot of these are real easy. The Semitic ones are fairly easy, except for Arameans and Lydians, because they're both F. There's an F and an F2. They're totally separate from each other, and I don't know which is which yet. I haven't looked into it. All this stuff takes time, to look at it and compare it and decide who is who and what's what. But G is pretty much, I had that pretty much from the beginning. That's Assyria. Elam is H. That's real easy because they're known people today. Cushites are known people today, but there's a lot of haplogroups in the area, including from Egypt, from Mitzrayim in the area as well. So we can't mix up, which I did at first. They have V32 and V12. They have Cush as V32, but V32 is in the same group as V12, which is Mitzrayim. So it can't be the same tree. It's got to be a different tree. So, and there is a lot more. There's a V or an M92 or whatever it is, a V6 or a V92 and a 281, but they're all like straggler lineages, which they haven't seemed to be able to put together, but they're all connected at some point, and they'll either connect to the Cushite lineage or Mitzrayim or the Phoenician North African lineage. Not the later Phoenicians, the first Phoenicians. But anyways, I'm doing all this rambling here for a purpose, because I want to get into some science. Of course, that is science, that biological science, haplogroups, genetic DNA doesn't lie. Of course, there's Israel, which is J2. Arabic is J1. Israel is also, parts of Israel are J1. Parts of it are Arabic. Parts of it could be Hebrew. Parts of it could be Moab. Could be a whole bunch of things. But then there's the lost tribes of Israel. The first ones that went is Dan. So turns out that I'm probably Dan, because they were the first ones that went into Europe and spread into Europe and named everything Dan. Um, so that's pretty much a given. So that's basically everything, all the haplogroups. But anyways, I wanted to get into this little notion of time and distance and space and measuring of time and stuff like that. Of course, the Bible measures time. Since there is no single rate of the passing of time, there's no single measure of time in the universe. There is, in other words, time is variable depending on how much matter is in the vicinity. That's how fast the rate of time is going to pass by. So, and it depends on speed and everything, the rate of time. It depends on your speed. It depends on a whole bunch of things. It depends on your perspective, all kinds of stuff. So, So the passing of time, biblically speaking, is one evening and one morning. That's one day. That's how we measure time. Keeping in mind that in the rest of the universe, there is no single measure of time. That same rate of time that we have is going to be different elsewhere in the universe. It's going to be run at a slower rate of time. It's going to run at a faster rate of time. Now we've known this and we've observed it, we've compared it, and we've verified it that time is relative to the amount of matter or gravity in the vicinity. Now, what we hadn't verified, what we just recently verified for the first time in our lifetime, is the variation of distance or the dilation of distance. What you call the variability of time is called the dilation of time. The variability of distance, the measure of distance, is called the dilation of distance. And that was never verified until they set up this interferometer and detected these black hole collisions. But in order to prove that it was the dilation of distance, they had to see an event. So they had a neutron star collision that they were able to detect in the interferometer, and through triangulation, they could tell where it would be in the sky. So they told all the astronomers around the world to look in that place in the sky, and they were able to observe the same event that they detected. There was a neutron star collision. Now, if that's all true, of course, seems reasonable. That would verify the dilation of distance. So, the dilation of the distance is a thing. In other words, a yardstick will be longer than a yardstick at sometimes, at some point, some places, and in other places it'll be shorter than a yardstick. The same yardstick. If you take the same yardstick, it's going to be longer in some circumstances and shorter in other places. And that was verified. That was detected with the neutron star collisions because they detected the collision, the gravitational waves through triangulation. They told people to look in the sky, and they observed the collision, the light, because when you have black hole collisions, there's no light emitted. But with a neutron star collision, they observed the light emitted, and they observed the formation of heavy metals, gold and silver and platinum and all that stuff. They detected it through the spectrolysis, spectrum analysis, and they were able to tell what metals were being formed and how much and all this kind of crazy stuff, which was a lot of gold, a lot of platinum, silver, the heavier metals. They observed in the neutron star collision. So it's a lot of stuff that's verifying for the first time or verified for the first time in our lifetime the dilation of distance, which we um, were, observing in other ways or calculating in other ways. So we have the dilation of time, dilation of distance. Now this gets interesting. What's up? I'm talking about science if you're interested, but it's very interesting. I like it. So we have verified that there's no single measure, single rate of the passing of time. There's no single rate of the dilation of distance. But if you're spamming, I think you're spamming. So, and I don't want to promote anything. I'm a Christian channel. I can't promote anything unseemly. So I guess I'll just have to and knock it out. Anyway, so we have the verified the dilation of distance, the dilation of time, and which is interesting when it comes to the measure of distance and time by way of light years. Of course, light years is a distance, but it's also a time. And this is a problem for a young Earth, if you believe in a young Earth. But, you know, uh, Jason Lyle seems to be confident that there there's a way to measure the one-way speed of light. That's a little bit iffy to me, but he's pretty confident about that. Other people seem to think that the speed of light is variable. The rate or the speed of light is variable. Well, it is and it isn't, because this is what it is. The speed of light is always 186,000 miles a second, or 300 or 3,000 kilometers per second. What is it? 3,000 kilometers per second, 200 something, 90 something thousand kilometers per second. Anyway, so it's 186,000 miles a second. So that seems right. 300 kilometers per second. So that is the speed of light that we see light arrive. Okay, that would be a problem for, you know, extreme distances, um, being able to arrive in 6,000 years, unless there's a variable, a caveat, which there is, because since we've verified, since we've been able to verify the dilation of distance and the dilation of time, then we have something to work with as far as the speed of light is concerned. But light always travels 186,000 miles a second. But the way you measure light is not constant. In other words, it's always going to be 186,000 miles a second. But what's variable is the second, and the distance is variable. So that would effectively change the speed of light relative to us, but without actually changing the speed of light. So it's always going to be 186,000 miles a second. But what happens is that where we are, there's gravity, and we can measure the speed of light, and that's what it's set at. That's the rate that we see light arriving. That's what we've measured. They have complicated ways of measuring the speed of light. They've measured it at that it travels 186,000 miles in 1 second, or takes 1 second to travel 186,000 miles. So that that would be a problem if everything was constant. Of course, the speed is constant, but it's the measurement of distance and the measurement of time that is not constant. So this is what we have to work with as far as understanding the age of the universe. Because remember, there is no single rate of time. There is no single measure of distance in the universe. We have an arbitrary measure of time, which is one evening, and one morning is one day. That's our measure of one day, 24-hour period. Okay, that's our measure of a week. That's our measure of a month. That's our measure of a year. Okay, so That's how we measure time. Okay, so if we're going to use that measure of time, how can it be that we can see starlight from stars many millions of light years away or whatever it is? It's supposed to be almost 13 million light years away or billion years or whatever. 13 billion years. Well, anyways, but that's assuming the rate of time that we have where we measure the speed of light as 186,000 miles a second, which it is everywhere in the universe. Everywhere in the universe, it's 186,000 miles a second, but it's the rate of time that changes and the measure of distance that changes. So the rate of time, the rate of 1 second, the passing of 1 second is not going to be the same. It's not always going to be 1,001 for 1 second. It's going to be 1,001 in some cases and 1,001 in other cases. In other words, the rate of time, the rate of the passing of time is what changes. What changes the rate of the passing of time is the amount of gravity. The more gravity you have, the slower the passing of time is going to be, the slower the rate of time is going to be. But it's always going to be 1 second. It's always going to be 1,001, no matter how fast that second passes. It's always going to be 1 second. But see, that's what happens when you say that it's always 186,000 miles a second. It's still not the same speed. It's still not going to be the same speed because the rate of time is never the same anywhere in the universe. So what happens is that when starlight leaves, or let's say we have an astronomical event, when we have an explosion in outer space somewhere, we have observed where there's an explosion in outer space, but in the vicinity or in the pathway of the explosion, the light from the explosion to reach us, it turns out that there's a lot of matter and a lot of mass in the vicinity that warps or dilates the time and distance or slows down time. So what happens is we have witnessed in outer space the same astronomical event. We have witnessed the same event multiple times in different places in the sky, the same event. In other words, you have the same event in different places in the sky multiple times, like 4 times or something. And some of the events will be years apart from each other, but it's the same event. So from this, we know what's slowing down light. I mean, slowing down time. We know what slowing down time is matter, the amount of matter in the vicinity. So, and it actually slows down the light by a factor of years. So you have the same astronomical event. You'll see it in the different places, different let's see, different place, years apart from each other, different places, the same event. In different different places, different the same event, different places, sometimes years apart from each other. Anyways, so from that we can know that what's slowing down time is the matter or the amount of mass in the vicinity is what slows down the time and what slows down the light from reaching us. So that's an unusual event that we've witnessed. We've seen it happen, but it's not very common. Most of the time, we just see stars, right? We'll see stars, we'll see starlight, and and that's it. So, what what happens if there is, let's say, there's a single star out there? Say it's at the edge of the universe, or let's say it's a galaxy. So let's say it's a galaxy at the edge of the universe. You know, 13 billion light years away, or whatever. 13 billion years away, whatever. That's what the estimation is. Okay, suppose, let's say there's, let's say there is, but we can see the galaxy, right? Between us and the galaxy, what's between us? In most cases, or in many cases, in a lot of cases, there's nothing between us and that galaxy. So that means there's the void of space in between us and that galaxy or that star, whatever. And that also means that there is no matter in the vicinity of the photons from the galaxy reaching us for most of the distance. Now, what does that mean if there's no matter to slow down time for most of the distance of the starlight reaching us? It means that there's nothing to slow down time, because what slows down time is matter. If there's no matter in the vicinity between that star, that galaxy, and us, there's nothing to slow down the time. That means that time is going to pass by at a very fast speed, very fast pace. In other words, a second will be, instead of being 1,001, it'll be 1,001, even faster. It'll be a fraction of a second. A second will be a fraction of a second relative to our rate of the passing of time, where we are, where there's a lot of matter in the vicinity that slows down the rate of time. But in the void of space, there's nothing to slow down the rate of time between that galaxy or that star and us. So for most of the trip, it's going to be traveling 186,000 miles a second, but they'll be very fast seconds, because we've already verified that that it's matter that slows down time. If there's no matter in the way or in the vicinity, it's not going to slow down time. That means that time is going to run at a very fast rate. Distance is going to be at a greater distance, and that's why they're so far away. But it also means that the light is going to reach us basically instantaneously, since the photons have no mass of their own. They experience no time. So for most of the trip, they're going to be traveling the speed of light, which is instantaneously, because in through the void of space, there's no matter to slow down the rate of time. So basically, that's my ramble, um, and that's how we can see the stars in in a universe that's 6,000 years old. Because for most of the distance, the rate of time, there's nothing to slow down the rate of time in the void of space for the photons between the galaxy or the star and us. Because when there is matter to slow down time, we'll see the same astronomical event in different places years apart from each other. Years apart. That's how much it can slow down the light, the speed, or the because it doesn't. it doesn't slow down the light. It slows down the rate of the passing of time. So if it slows down the rate of time, it effectively changes the speed of light. It will slow down the speed of light. It'll delay the light from reaching us, which is observed. It's an observed phenomenon where we'll see the same astronomical event in different places years apart from each other. The same event. So we know that it's matter that's slowing down the time, the rate of the passing of time, and slowing down the light from reaching us. So where there's no matter, there's nothing to slow down the time. So that means that the starlight reaches us instantaneously, and by the time it reaches a place where there is gravity, it's still going 186,000 miles a second anyway. But for most of the trip, the second is going to be a fraction of a second relative to our perception of the passing of time. But that's about it, and that's how we can see distant starlight in less than 6,000 years. So God bless everybody. Take care, and I just wanted to ramble a little bit on this topic. So that's it. God bless. Take care, everybody.